Deputy sir, your mobile is adjacent to you. Deputy sir, your mobile is adjacent to you.
Sanita ma'am.
Over to you, ma'am. And it is on due.
Let's start, ma'am.
Yes, ma'am.
Let's start, ma'am.
Yes, ma'am. Yes.
Good morning to all. We are gathered here on this Sunday for the generic talk series #28. Hereby, I call upon Mr. Jyoti Prasad to deliver the welcome address.
Good morning, everyone. It is my great pleasure to welcome you all on the topic networking fundamentals and data center design for 5G core. We are truly honored by your presence and we hope this session will be informative and inspiring and encouraging for all participants. I would like to express my heartfelt gratitude and our vice chairman, and I also special thanks to our principal sir, Dr. and I also welcome Dr. Ma'am, who is tirelessly putting analyzing this on behalf of all our management members. I welcome all the participants and guest speaker. Ma'am, over to you, ma'am.
Thank you, sir. I am very glad to welcome you, Sandeep, for this generic talk series 28 on the topic networking fundamentals and data core. The data center design for 5G core. Actually, we are really happy to have you here on this online session. And we hope that this session would be very much useful for our ECE students and all other participants who listens to this. Thank you for accepting the invitation.
The world is at its faster pace with automation and data everywhere, which reminds us of speed of communication. Here we are to listen to network fundamentals and data center design for 5G core from an eminent person.
Yeah, Sandeep.
Thanks, ma'am.
Yeah, Sandeep.
Thanks, ma'am. I hear a lot of echo. Do you guys hear it? Like, or can I
hear
get
a lot
started?
of echo. Do you guys hear it? Like, or can I
I
get
hear a lot
started?
of echo. Do you guys hear it? Like, or can I get
I'll
started?
keep others mute, Sandeep, so you can.
One minute, Sandeep, 1 minute.
Yeah, let me
1 minute,
join.
Sandeep, 1 minute.
Please let me know when I can start and.
Yeah, you can start now.
Please let me know when I can start and. Please let me know when I can start and. Please let me know when I can start and. Please let me know when I can start and. Please let me know when I can start and. Please let me know when I can start and. Please let me know when I can start and. Please let me know when I can start and.
The participants can mute the live streaming if you have it in the another tab. Participants can mute the live streaming if you have it in the another tab.
Or you switch off it for live streaming. இப்ப எக்கோ வரல ஜெய் ஜோதி பிரசாத்
இப்போ எக்கோ இல்ல மேடம்.
இப்ப எக்கோ இல்ல ஜோதி பிரசாத் உங்களோட தான் எக்கோ ஆகுதுன்னு நினைக்கிறேன். ஓகே இப்ப வரலையே எக்கோ வரலையே. ஓகே சந்தீப் now you can proceed please. Okay Sandeep now you can proceed please.
Okay, sure.
Okay Sandeep now you can proceed please.
Okay, sure.
Okay Sandeep now you can proceed please.
Okay, sure.
Sandeep now you can proceed please.
Okay, sure.
Sandeep now you can proceed please.
Okay, sure.
Sandeep now you can proceed please.
I still hear a lot of
I
echo.
guess there is an echo from your side.
Yes 1 minute. Sandeep I think yours. Hello Sandeep.
I think echo is from his side, ma'am.
Sandeep, right?
Yes, ma'am. When he
Yes.
ons it,
It is coming. Yeah, echo is coming.
Our talk is retransmitted.
Okay. Sandeep, can you check your side? Sandeep, can you check your side?
Yeah, I'm still hearing the echo.
Check your side.
It's just repeating over and
still
over.
hearing the echo.
It's just repeating over and
I'm still
over.
hearing the echo. It's just repeating over and over. I'm still hearing the echo. It's just repeating over and over. I'm still hearing the echo. It's just repeating over and over.
Sandeep, sir? That is, if you are able to join from any other device.
If you are able to join from any other device.
Sure, let me join.
Sir?
Yeah. Are you guys able to hear me now?
Yes. I think there's no.
No issues. Okay, proceed, please.
Yeah, sure. Thank you. Let me share. Yeah. Are you guys able to see my screen now?
Yes, but
Yeah, okay. Thank you. So the topic for today is networking fundamentals and data center design for 5G core. The topic sounds very elaborate, but don't worry. We will be looking at a specific real world use case on how a data center design is currently made for that use case, as well as like how 5G core is involved in that use case. And we will start looking at breaking it down by looking at the networking fundamentals for it. Okay. Moving to the next slide. Okay, to start with, why learn from me, right? I was a 2017 graduate from R.M.D. I'm an R.M.D. alumni. And one of the things that motivated me or made me passionate towards networking is like I completed my CCNA in 2016, scoring a perfect score there. And I also started teaching networking for working professionals back in 2016 when I was actually in my third year in networking. That motivated me towards networking, and I eventually did my master's in network engineering at the University of Colorado Boulder, USA. I got an internship at HPE as a network automation, and that eventually helped me land a job at Cisco, which was my dream company, as a network software engineer. And I have been with Cisco for the past 6+ years, working on 5G core, designing data centers worldwide, like in Europe, in USA, and Africa, and other places. I'm here to bring in my experience that I have learned for the past 6+ years through this session, and in the future sessions whenever I can. My goal is like if I can motivate even 5% of the people that is attending this, that would be a great success for me, because that's what happened to me. I back in 2016, and I want to give it back to the students here. So if you have any questions, please comment in the live chat that is available on YouTube. I will try to look at it and answer your questions. We'll try to make it as engaging as possible, so that it's not just a one-sided conversation. Thank you. So the agenda for today is we will look at why learn networking. So how is it going to help us in the future, right? Because anything we learn shouldn't be just going for you based. So we'll first look at why we learn networking, and we'll look at it from a real world perspective, which is going to be a connected cars use case. And then we will look at some basic 5G network functions that is in use today to make this connected car use case and any other use case for 5G possible. Then we will look at how these 5G network functions are deployed in a data center and how the connectivity for them happens. So to make this all possible, we need to know the fundamentals of networking, because that's where everything begins. So we will look at some of the networking fundamentals. We will not be able to cover everything in today's session, but again, I'll try to cover as much as I can in today's session. Okay, going to my next slide. Okay, so why learn networking, right? If you look at the first slide that I have put here, you might recognize some of these, like ChatGPT or Claude or Gemini, right? So what is one thing that is common in all of these? These are all AI applications, and these are all the trending AI applications that many of us use today or heard about it and all, right? So to power all these applications, what is one thing that is needed today is data centers, racks and racks of servers and compute. And to give compute, to give power for these AI applications, we need data centers. And to maintain these data centers and to automate these data centers, we need network engineers. And that is where networking comes into place, and that is where networking is going to trend in the future. If you see on the third picture, it is me and my friend Arun, who now works at Netflix. So we two are actually building a data center at our university, probably sitting late night and working on it. Yeah. So this is one of the use cases I want to put strongly towards why you want to learn networking, because AI is the future and AI is going to demand more compute, and more compute means more data centers, and more data centers requires more network engineers to manage these data centers. Okay, moving to the next slide. So this is an interesting use case that I, for the past 4+ years, have been working on as a part of our team. This is actually a $1 billion business for us, and I want to break it down at a very high level. This is not like, I'm not going to go deep inside it, but I'm going to touch at this like at a very high level. The leftmost picture that you see here, you might be aware or you might not. Like, this is the Tesla car that you see over here, and all these Tesla cars, when they power up first, what do you think happens? Each of these Tesla cars have a eSIM in them or a SIM in them, like similar to how our mobile phones have a SIM, right? So these Tesla cars are similar to a computer or a mobile phone. So in terms of how they get connectivity. So these SIMs reach to the nearest tower to get connectivity. On these towers, these antennas that you see here, or you can, in 5G terms, you can call them RAN, radio access networks, connect to the telecom data centers. So if these eSIMs are, let's assume these are Airtel eSIMs, right? So they go to the Airtel RAN, which directs them to the data centers which Airtel has connectivity with. Let's assume for this use case that Airtel has a partnership with Cisco, right? So Airtel is going to direct their requests to the telecom data center that is managed by Cisco. And in these data centers, the blocks that you see, these 5G network functions, are going to be running. Some of the common popular ones for 5G network functions are like SMF, AMF, AUSF, UDM, PCF, and UPF. These are going to be deployed in these data centers. So when the connection reaches these data centers, right? So they're going to be authenticated, and then a session is going to be established, and then sorry. Okay, so a session is going to be established, and then there is going to be policy functions like QoS that is going to be set up for these sessions. And then the traffic is finally going to be directed to the, if it's a Tesla company's cloud. So once that is directed here, Tesla has its own applications like Tesla Maps, like similar to Google Maps, right? Tesla has its own maps. Tesla has autopilot features, autopilot applications, supercharging to provide charge for these cars, right? It's supercharging applications and all. So when the connectivity reaches from the eSIM, it is going to be directed to the RAN, which is eventually going to be sent to these 5G telecom data centers, which is going to be sent back to the car company's cloud. And from there, it is going to be routed back to the car itself. So this happens over and over, which powers these cars, like in terms of providing all the features that the Tesla car itself has. So this is where you can see like how 5G is useful, right? So before I go into brief details of how these network functions work, I want you to understand the flow here on how these network functions are deployed in these data centers. If you have any questions, feel free to ask. Okay. Let's break down these network functions itself, right? Okay, so when the connection first reaches from these eSIMs, right, what do you think first happens? First, there's going to be an initial registration, and the sessions are going to be kept alive as the car moves between towers. So a car is not a stationary object, right? It is going to keep moving. As it keeps moving, we need to keep registering at the specific location, and the handoff needs to happen. And that is maintained by the AMF here, the Access and Mobility Management function. And then once the car connects, and the car needs to be assigned an IP address. An IP address is going to be, so SMF here is going to assign it an IP address from its IP address pool. Once it gets an IP address is nothing but, like, you can think of it like just a unique name for a specific user that comes into the network, right? And then once the IP is assigned to the Tesla car, right? We also need to actually, before we even assign this IP address, we need to make sure that the SIM, when it tries to connect, we need to validate whether that SIM is actually allowed in our network, and that is the function of UDM or AESF. So UDM or AESF acts like a traffic guard, or you can say like a police, right? Like it makes sure the SIM is actually who it says it is. Once that is made sure, the SMF is going to assign it an IP address from its pool. And once that IP address is assigned and the connection comes back again from the SIM, right? The UPF, which is the data plane function, it is going to take care of routing that request from the SIM to the car company's cloud, and also getting it back from the car company's cloud back to the eSIM. That is how the data path works. And the SMF here, it acts as the control plane to make sure, like, when a request comes in and it belongs to a particular stream, right? It is going to send it to the UPF, and the UPF is going to take care of the routing part. What is PCF here? What does PCF here do, right? It is a policy function. So what does policy function actually mean? Like, Tesla might send different requests, right? Like one for autopilot, one for streaming videos and such, right? We need to decide which functions we prioritize, which functions which we don't, right? Like autopilot is going to be our first priority because that is the one that is navigating the car itself, like which turn it needs to take and things like that, right? Because it's self-driving, right? So that gets prioritized first as by the PCF, whereas like things like streaming videos or playing games that the Tesla requests, right, is going to be prioritized next. So that we can set by the policies in the policy and charging function itself. So these are very I touched upon these network functions at a very, very high level, like 10,000 feet level, right? There are much more things that happens actually, but for this presentation, I'm going to go into more details on how these network functions are actually deployed in a data center, which is what this session is about. And when they are deployed, what are all the networking fundamentals that comes into picture? Any questions here? Please let me know. If not, I'm proceeding to the next slide.
Participants, if you have any questions, you can ask.
Okay. Okay, so moving on to the next slide, right? So this is where we are going to see this is again at a very high level how these network functions would be deployed on a data center, right? So think of as I talked before, a data center is nothing but racks and racks of servers, switches, and routers deployed together to give us the compute that is needed to power these applications. Like the applications in our case for 5G is going to be SMF, AMF, PCF. All these applications, when they are deployed, needs to be running on a specific server, and these servers needs to be connected by using switches, and the switches eventually needs to be connected by using routers or layer 3 switches, and there needs to be a firewall that takes care of making sure we only allow specific requests, and there also needs to be a load balancer which makes sure the requests are going to be spread out across all these servers so that we efficiently manage all the requests that is coming to our data center. So this is what is going to be deployed in a data center. So think of this, right? So we have 2 racks of servers. So that is what I have separated by using a dotted line here. So the first rack is going to have 2 leaves. So when I mean leaf switches here, right, like I have depicted by just a block, but we will see in the next slide how these actually look. But think of here, this leaf 1 and leaf 2 is just going to be a switch, right, a network switch. And spine again is going to be a layer 3 switch. So there is 3 switches here deployed, and there are multiple servers here deployed, right? Let's first see how these leaf switches are connected to our spines, right, that you see here. So each leaf switch is going to be connected to 2 spines. The reason we make it this way is, like, let's say even one of our spine goes down, right? We still don't lose connectivity because we will have the other spine through which we can route our packets. And this is the reason why each leaf that you see here in this case, like there are 4 leaf switches, right? Each leaf switch is going to be connected to both the spines. And that is all the connections that you see. If you see here, leaf switch 1 is connected to spine 1, and it's going to be spine 2 actually. Spine 1 and spine 2. Similarly, leaf switch 2 is connected to spine 1 and spine 2, and similar way, leaf 3 and leaf 4 as well. So once these are connected together, right, we come to the server part. Each server is going to be connected to at least leaf 1 and leaf 2, which is in the same rack. The reason again is the same. Like if we lose connectivity to one of the leaves here, we still can route the packets through the other leaf. These servers are going to have redundant ports. So if in this case, let's assume there are 2 ports here, right? One port is going to go to one leaf and the other port is going to go to other leaf. So even if the server's first port goes down, we still can route the packet to the other leaf. So similar way, all these servers are connected, right? And on these servers, we can deploy multiple things. One of the things is like we can deploy the Ubuntu directly on it, like an Ubuntu host OS directly on it, right? Or we can deploy a VMware ESXi. I'm sure like many of you here would have heard about the term VMware, right? Like so VMware ESXi is nothing but like a hypervisor which sits on top of the server, which helps deploy multiple VMs on top of it. So instead of us deploying a single Ubuntu OS, right, we can deploy multiple Ubuntu VMs. And these VMs can run network functions or like KVM VMs. So you can think of each Ubuntu VM can be a UPF, right? So actually that is very similar to how we do in the industry right now, right? So a server is a bare metal, on top of which you deploy a hypervisor, which manages the server's compute resources like the CPU, memory, storage space, which is the hard disk. And this ESXi is going to allow us to deploy multiple VMs on top of it. This is one way of doing it. There is a more advanced, or I would say a more better way of doing it, which is deploying Kubernetes or Docker containers on top of it, right? So on these servers, we can deploy Kubernetes or Docker containers, and on top of, and once the Kubernetes container is deployed, right, like we can create namespaces where we can deploy different 5G applications, right, like SMF, PCF, you name it, like UDM, UDR, and things like that, right? So this is the way we are going to deploy for, let's say, first 3 servers is going to have all the network functions that we need. So what is the use case? How will the connection reach outside? So that is where a firewall comes into picture. This leaf 4, if you see, is connected to a firewall, right? So what is the function of a firewall? Firewall is nothing but, you can think of it like a watchman for your apartment, right? Anything that needs to go out or come inside, any traffic that needs to go out or come inside needs to pass through this firewall. And we set a set of rules here saying you only allow these kind of requests. You only allow a request that is coming from a K8s pod, whereas you block a request that is coming from this specific Ubuntu VM. We can identify these requests by using either the IP addresses or port numbers and things like that. So details of which we will try to see in this session or upcoming sessions, like whenever possible, right? So, to summarize the basic functionality of firewall, a firewall is nothing but like going to allow certain requests, whereas blocks certain requests. Similarly, it is also going to allow certain requests from the internet, whereas block the others. Yeah. So what we see here is whenever a request comes from the eSIM that we saw in the Tesla, right, through which is nothing but the internet, the firewall is going to either allow it or block it. If it is allowed, it is going to go to the leaf switch here that you see here, right? Once it goes to the leaf, any other server that you have, like you can have, I have shown here 4 leaves, right? There can be hundreds of leaves in an actual production data center. But any of the servers that is connected to these leaves is going to be 2 hops away. What do I mean by a hop, right? So in this case, when a server under leaf 3 wants to reach leaf 1, this server is 2 hops away. Because why do I say that? Like, because the connection needs to go to leaf 3, then it needs to go to spine 1 and leaf 1. So you see here there is leaf 3 to spine 1 is going to be 1 hop, spine 1 to leaf 1 is going to be another hop. So this is going to be the case for any server in this network, even if you have hundreds of leaves. That is the power of spine leaf architecture. The time it takes to reach any server with any other server in the network is 2 hops always. So that the traffic that you see here is east-west traffic, like where one server in one server connected to one leaf, when it tries to reach the other leaf, other server in another leaf, it is always going to be 2 hops away, and the traffic that flows between them is nothing but an east-west traffic. Whereas the traffic that is coming from the internet or going to the internet is going to be a north-south traffic, because it is traveling out of your data center to the internet and coming back from the internet, right? So a data center typically has 2 kinds of traffic, which is east-west and north-south traffic. East-west traffic is nothing but all the traffic that happens within your data center between different racks in your data center. Whereas a north-south traffic is nothing but like any kind of traffic that leaves your data center towards the internet and comes back from the internet towards your data center. And any east-west traffic between the data center is always going to be 2 hops. So we have a predictable latency, and we also maintain availability where, like, in case of any leaf goes down, we always have a redundant leaf that is going to take care of the functions. So this is how a data center does things at scale, where it can cater to millions of connected cars or millions of IoT devices at the same time, while maintaining availability, redundancy, and a predictable latency. And this is what is currently used in data centers, like what is used for like OpenAI or all these companies that you see which run AI infrastructure, right? When they mean like they are all the prompts that you type in your ChatGPT or any other AI applications, right, is going to be processed by the data centers like these, which are deployed in remote locations. There's going to be at least like racks and racks of data centers, and I actually work on deploying these kind of data centers today through automation. So when I say like we deploy these data centers, right? Like we do not go and manually log into these switches or configure these switches or configure these routers, right? The reason is like everything today is automated. So that is where, as a network engineer, you need to know how to automate stuff. You need to know software. So if you truly want to be a network engineer today, you need to know how to code. You need to know how to automate things. But before you go there, you need to understand the basics of networking, which is the fundamental necessity to be a network engineer. Um, any questions here on the data center infrastructure architecture that was talked about here? Okay. Yeah, feel free to even send me an email or just send me a message on my phone, like even after the session, right? Like if you want to learn more about networking, or even like how to land a networking job, or like things, anything like that, right? Okay, so in the previous slide, we talked about blocks, right? Like we did not really understand how these actually look in the industry today, right? So that is what I have shown here in the pictures that you see here. If you see here, the first picture shows the spine nexus switch, right? You might ask, what's the difference between the switch that I see on the left side versus the switch that I have shown on the right side, right? Like both look very similar. It's just, if you see here, the ports here, the size of the ports here are different, right? And the number of ports are also different. On the leaf side, you might see more ports, and each of the port is actually smaller. The reason for this is these leaf switches connect to the servers directly, right? So when a leaf switch connects to the server, the port itself can be the port capacity itself can be lesser than what it actually when it actually connects to a spine. Spine ports here the total number of ports might be less, like just 48 ports or something like that, right? And each port might be a 100 gig port. Whereas in case of a leaf switch, the number of ports might be more, like 96 ports in total, whereas each port will be a 25 gig port compared to the 100 gig ports on the spine. The reason is these connect to a server, which individual servers which don't need that much of a capacity, whereas when it actually connects to a spine, right, we need fast networking. That is the reason when it connects to a spine, we use 100 gig ports here. And you see these leaf ports connect to the spine by using the ports, the 6 ports that you see here. And these are going to be again 100 gig ports. Both are Nexus switches, but there are many other, apart from Cisco, there are many other companies like Arista or HPE, which makes these switches today in the data center. This is one of the examples of a firewall router, right? When you look at it from outside, it doesn't look any different, but the functionality that it does is going to be very different, which we'll try to see in future lectures or here if possible, right? But again, the number of ports that you see on a firewall is going to be very less when compared to a spine or leaf. This is because the firewall is not connecting to multiple switches or anything. It is going to be connecting to 2 switches or 3 at the max, and it's going to route the things to the internet. And this is an example of a UCS server, right? These are examples. This is an example of a Cisco server, but there are many other companies of servers as well. All these blocks that you see here are nothing but storage, right? Each block that you see here, it can be like an 800 gig capacity SSD. So you can imagine the total capacity. It might be in terabytes here. And the ports for the server is going to be at the back, and it's going to have like 1 or 2 ports at the max. And the body itself is going to be called a chassis, right? So these are all the industry terms, right? Like the body is called a chassis, and you don't call a cable in this case, like we saw the cable. You don't call them wires, you call them cables. If you want to stick to the industry standard, right? Okay. So this is all I wanted to cover in terms of like at a very high level, like the use case level. So let's try to dig a little bit deeper into the networking fundamentals itself. Unless anyone has any questions here. Okay. Okay. So this is this picture. I'm sure everyone would have seen it, like in our networking class or the networking fundamentals class, because this is a very classic picture that any networking class is going to cover for you, right? But I would like to talk about why a TCP/IP stack is useful, right? Or a OSI model is useful, right? OSM model talks about like all these layers, right? Like physical data link, network transport, session, presentation, application, right? But what's currently used in the industry is something which combines them into four layers, where physical and data link is combined to a network access layer. Network is nothing but an internet layer. Transport is transport, and all these three is combined to an application layer. So where do you use it, right? When you're designing anything in networking, right, you need to think about all these layers. Without understanding these layers, right, you would not be able to design a data center or like leave a data center. Just designing how to connect these two computers in your lab by using a switch or a router, you need to understand this, without which you would not be able to communicate between one computer to the other. Um, so or if, let's say, computer A, which was talking to computer B, suddenly loses connectivity, right? How do you troubleshoot? Um, Again, you need to involve all these layers. You need to either start from top down, or you need to start from bottom up. So what do I mean by these, right? So let's say computer A, which is talking to computer B, suddenly the link here goes down, right? If you start from top down, right? Let's say this is a client and this is an HTTP server here, right? So how do you start troubleshooting? You first start checking the application layer. When you start checking whether your application, the client, is actually pointing to the right HTTP server. You check the configuration itself. You check the IP configuration. You start checking the port configuration. So that is at the application layer itself, right? You then move to the next layer, which is transport. Uh, Transport layer involves two major protocols, which are one is going to be TCP, the other is going to be UDP, right? If, let's say, this model is using TCP, right, you start checking things which are particular to the TCP itself, like the window size, whether there is any congestion, and things like that, right? So what I'm trying to say here is, it's not enough for us to understand theoretically what an application layer means or a transport layer means, right? We need to understand what applies, what do we mean when we say an application layer? What are all the things that happens at the application layer? When I say transport, what are all the things that applies? In this case, in case of transport, is going to be TCP or UDP. Where is a TCP used? Where is a UDP used? Like, once we understand that, right, like this would be really helpful. And this is something, even though like even a network architect who is designing an AI data center uses today. So please don't take this lightly, because this is the fundamental layer, because using which anything is designed today or troubleshooted today. Okay. Yeah. So one more, before I move to the next slide, one more thing which I want to touch here is, right. So I mentioned this is nothing but a client, and this is nothing but a server here, right? When a packet is sent from the client, what happens here, right? So let's say we are using a client like a Postman, or like, let's say we are just sending a curl request, right? I'm not sure if you're familiar with either, but what I'm trying to say here is, like, let's say, okay, so we can even think of client as a browser that we have, right? Like a Google Chrome browser. So whenever we try to type www.google.com, right, we are trying to send a request. So the request passes from the application layer to the transport layer. So a packet is going to be constructed, which just has the application layer bytes, and then a header is going to be added. What do I mean by header, right? Header here, you can think of a header like adding contents to a mail, right? Like, so in case of when we send an email, right, we have different headers like from address, to address, subject, and then data, right? So think of application as the data, and then you start adding layers on top of it, right? Like subject, from, to, and things like that. So in similar way, we have the data, the application layer, we start adding the transport layer, which can be either TCP or UDP. In case of a browser, it's mostly going to be TCP. So we start adding the HTTP layer on top of it, saying these are the ports that are going to be used. In my case, I can say like I have, let's say, port 223, whereas my application or HTTP server is listening on port 443 or port 80, right? So I'm going to say my source is 223, whereas my destination is 443. So that is the layer that I'm going to add on top of it. The internet layer talks about the IP addresses itself. If my IP address, let's say, is 1.1.1.1, right, and the and my destination is 2.2.2.2, right? So I'm going to add the source and destination at the internet layer. So what happens in the network access layer? So here is where I add the frames. So anything that is transmitted in the cable can only be transmitted in zeros and ones. You know that, right? So it's going to be electrical signals. So it is converted into bits so that like the data can actually be sent, and data can be actually sent on the cable itself. And we also add error checking. So we say like this packet has this as the CRC, so which is nothing but like as a way of error checking. So in case when the packet is actually sent in the wire, if it gets corrupted, this computer can actually verify that's whether it's corrupted or not by verifying the CRC itself. Yeah, so this is what happens when the packet is actually sent. The packet is constructed from the application layer to the network access layer, and the packet is finally prepared and sent over the wire. When the other computer receives it, right, so it is going to do the same work in the opposite direction. It is going to receive the bits. It is going to de-encapsulate the packet to see the frames, what is the IPs that, whether the IP actually belongs to, whether the destination IP that is mentioned in the packet actually belongs to it, and whether the transport layer that is mentioned, the ports that is mentioned on the packet actually is what it's listening to, and whether the application, it has the actual application, and then it's going to respond back. And the same process happens over and over. If you have any questions, let me know. Yeah.
Participants, students from Hutchison. Any doubts you could ask?
Okay. Okay. Moving on to the next slide. Okay. So again, I would like to give a real world example here, right? So let's take our computer lab that we have today in our university, right, where we have multiple computers, and each of these computers are sitting adjacent to each other, right? How do you think these computers are connected? These computers all connect to a common switch, most likely in our lab, right? So and this kind of a setup we called a LAN, which is nothing but a local area network. So these computers can talk to each other, send information between each other by using this switch, which acts like any packet that wants to flow between a computer A to computer B, right, needs to flow through the switch. And the switch makes the communication between them happen. To make this communication happen, there are multiple things you need that needs to be assigned at the computer's level, as well as needs to be configured on the switch level itself. Let's see first what needs to be assigned to the computer itself, right? So think of a scenario, right? Like where there are here, like let's say there are 4 people here, right? How do you identify each one of them? By using their name, right? So similarly, each computer needs a name. So which is nothing but it's going to be its MAC address. MAC address is a permanent address, permanent name that is assigned to the server's ports itself. So these MAC address will never change, and you can use them to identify the computer in the local area network. Um, so, so what is the purpose of IP address if we already have a MAC address here, right? So MAC address is going to be useful in case of identifying this this computer in this particular network when there are multiple networks in the picture. So IP address changes when the computer moves from one network to the other, right? So yeah, in this case, the computer is going to be stagnant, but think of a mobile phone, right? Then it connects to one network where when you have it in your, let's say in your university, it's going to have one IP address, whereas when you actually go to your home, right, it connects to your Wi-Fi, home Wi-Fi, right? In that case, it will have a different IP address. All I'm trying to say here is an IP address moves from network to network, whereas the MAC address is actually going to stay the same. So when you want to identify a computer in a particular network, you use the MAC address, which is similar to the name that we all have. So again, so we have the MAC address, we have the IP address. What is the purpose of VLAN here, right? So let's say we just have a single switch and we want to separate these 2 guys from these 2 guys, right? Like, so we want the person A here to communicate to person B, whereas we don't want the person A to talk to person C or person D here. How do we make that segregation? All we have is just a single switch, but still we want to make that segregation, right? So that is where VLAN or a virtual LAN comes into picture, right? What does a virtual LAN segregates a network virtually, even though there is just a single physical switch. So when you assign a VLAN to a particular computer, it can only talk to any other switch in the same VLAN if it's a layer 2 switch. If it's in a local area network, all the computers that have the same VLAN can talk to each other. Whereas when you assign it to a different VLAN, you are virtually segregating them from virtually segregating them to be a different network. So we briefly touched upon what is a MAC address, IP address, and a VLAN here, right? So these are 3 basic things which are necessary in a local area network. MAC address is a permanent address that you assign to a computer. An IP address is used to identify a computer in a particular network, and it can change per network to network. A VLAN is used to virtually segregate a computer so that like you can have multiple small networks within a big network. Hope I make some sense. Yeah. So you see here how a MAC address actually looks like here, right? A MAC address is, as you can see from here, it has 6. It is divided into 6 segments here, right? 1, 2, 3, 4, 5, 6. The first 3 segments are the organizational unique identifier. So as I said before, MAC address, it's tied to a particular port, right? These ports are actually designed by a particular company. Let's take Intel, right? Intel is designing a network card which has multiple ports, right? So when Intel gets MAC addresses from a centralized authority, right? They give Intel these first 3 bytes. The next 3 bytes, like or next 3 hexadecimal entities, can be assigned by the Intel itself based on the number of NIC cards or number of ports it has. So first 3 is going to be fixed, and Intel can assign the rest of the other 3. For our use case, we can assume that MAC addresses are always going to be constant, and it's going to be per port for per computer. As I said before, you can use VLANs to virtually segregate virtually segregate different networks. You can say these particular set of ports are going to belong to VLAN 10, whereas these particular set of ports are going to belong to VLAN 20. So if you have a computer connected in VLAN 10 and another computer connected in VLAN 20, you would not be able to talk to them on a layer 2 switch or a local area network until you have a router in place, which we will touch in the upcoming topics. Okay, so this is all I wanted to cover in the network access layer, or layer 2, you can call it, right? Okay. So before we move on, I would like to show you a small demonstration itself, like how this works, right? So let me try to open something here. Most out of time, but let me. Okay, so one of the common tools that a basic tool I would call, like any network engineer should be able to use, is Cisco Packet Tracer. I'm sure many of you would have used it here, right? So here, all I'm trying to show is a very basic local area network, right? Where a single switch connects to two PCs. Let's see the things that we talked about today, right? So I'm trying to log into this PC here. Go to the desktop. I show you the IP configuration that I have here. So the IP that I've assigned to this PC is 192.168.1.2, and I've set it, and I haven't set any default gateway, and I've set it to a specific subnet mask. So what does the subnet mask here depict is like anything that says 255 is going to be the network bits, and anything that says 0 here is going to be the host bits. So this IP belongs to 192.168.1.0 network. I would probably talk about subnetting more in detail later, but all I would want to think here is like this PC belongs to 192.168.1.2 network, and the second PC here that we have here belongs to 192.168.1.3. And it has an IP address of 192.168.1.3, and it belongs to the same network because the network here is as well like 192.168.1.0. So these two PCs are in the same network, right? And let's try to ping them. So we get a reply, right? So what's actually happening here? Okay, so this is its own IP. Okay, so we are trying to ping from this guy, which is 192.168.1.3. It has an IP of 192.168.1.3, and we are trying to reach 192.168.1.2, which is this IP, and we get a reply from it saying, "I'm reachable, and this is the time it takes, which is less than 1 millisecond, and this is the TTL it has." I'll try to touch TTL later, but all I want you to understand here is the communication happens, right? How does this communication happen? That's the reason is we have a switch here, which knows this PC is in this this PC is connected to this port, and this PC is connected to this port. How does it understand that, right? The reason is because it stores something called as a MAC address table. You see here, right? What do we see here? This is FA0/1 port. It says this MAC address is connected to FA0/1, and it has a VLAN 10. It also knows that FA0/2 has this MAC address, which is nothing but this PC. So when this PC tries to send a ping, right, and reaches the switch knows already that this PC is in this MAC address, and it forwards the request. And when this PC replies, right, it again knows where to send the request back. And that is made possible because the switch builds a MAC address table by mentioning the MAC addresses and which ports they belong to and which VLANs they belong to. If I put this port in VLAN 20, right, the same communication will not happen. The ping will not happen. That's because we are segregating these two ports into different VLANs. We are trying to say this belongs to a different network, whereas this belongs to a different network. And this layer 2 switch doesn't know how to communicate between them. And that is where we need a router and and more than that, actually, a routing table and things like that, which I'll try to talk later. But I think I'm almost out of time here. So if you want to learn more about networking itself, right, like hands-on, reach out to me further. I'm happy to help. Like my main motivation is like there was someone who actually helped me when I was in my third year at R.M.D. I would like to give back the same to each and every one of you who is interested here. Thank you.
Sandeep, do we have this Cisco leaf switches available in this packet tracer? And do we have any provision to design there?
So you mean leaf switches? You mean like layer 3 switches, sir? Or so we have switches here, right?
Yeah.
So if you see here, these are all the switches that is available here. So there is a layer 2 switch or a layer 3 switch you can add.
Okay.
If you take the data center level switch, if you're asking about a leaf switch, like a data center level switch, it is not available in the packet tracer itself.
Okay.
Because packet tracer, again, is not designed for a data center level networking. It is designed for a beginner network engineer to understand networking itself.
Okay.
But yeah, but I believe like for CCNA, if you want to understand up to the level of a CCNA, right, like you would not need a data center level switch. But there is a software called EVE-NG, similar to packet tracer, where you would be able to add a data center level switch itself.
Okay. So is that an open source? Can anyone use it?
Yes. EVE-NG has a community edition.
Okay.
Which it only works on a Windows PC. If you have a Windows machine, right, like you can download the community edition, but it's a little complicated to set up itself. It's not as easy as a packet tracer.
Okay.
But you would be able to set up like a data center level switch there. Yes.
Okay.
Yeah. Any other questions? There are more things I wanted to cover, but yeah, I think I'm out of time here, right? Yeah. Okay. So only thing I want to end the presentation with like is just a code that I really try to follow. If you're not enjoying the journey that you're going through, right, you probably won't enjoy the destination. So whatever you're trying to do, try to do it with passion, right? Like, uh, uh, to give context, like I was not like the top student in our class or anything like that. Like I was just passionate towards networking, and that helped me get here. So whatever you're learning today, try to be passionate, and I'm sure like that would take you places. Thanks, everyone.
There is one question in the chat box.
Yeah.
One Ms. Gunamati has asked, like, why do we need two address like IP and MAC? We can uniquely identify the device using MAC. Why IP is needed?
Yes. So what we saw was a local area network, right? Like where everything was combined in a single network. Whereas if you think of internet, right, like internet has multiple networks. So when one network wants to reach another network, so every PC in every network can't know everyone's MAC address. So that's the reason we have IP address. IP address will help us get to the network, and inside the network to identify a device, we use MAC address. So let's say we have R.M.D, one of the institutions, and R.M.K, there's another institution, right? When a PC in R.M.K wants to reach R.M.D, right, it uses its IP address. So it knows the IP, the specific IP address is there somewhere in R.M.D. So it will forward it to R.M.D. When it reaches R.M.D, right, the specific PC itself is identified by using the MAC address. So you need both. So one is to reach the R.M.D, and the other is to connect to the specific PC inside the R.M.D, which is by the MAC address. Um, hope that answers the question.
Yeah, thank you, Sandeep.
Yeah,
Any
if
other
you have more,
questions?
yeah, go ahead.
Yeah, students, if you have any other questions, please post it. Hope there is no
Participants
other
from
questions.
HSN can ask their questions. If they have any doubts, they can.
If no questions, we will close the meeting. No? Yeah, please proceed. Anita, please proceed.
Yes. Thank you, sir, for your valuable talk and insight into the network fundamentals and data center working. So it was nice hearing you, and also that practical session which you gave, that was very nice. So it's time to acknowledge the minds behind the program. Mr. Karpaya will make us look into the behind the talk. Please, sir.
Yes, ma'am. Thank you. Good morning to everyone present here. On behalf of R.M.D. Engineering College, it is my privilege to deliver the vote of thanks for today's generic talk series number 28 on networking fundamentals and data center design for 5G core. First and foremost, I express my heartfelt gratitude to our distinguished guest, Mr. Sandeep S, Senior Software Engineer, Cisco, California, USA, for taking time out of his busy schedule to share his expertise with us. Your insights into networking and data center design have indeed enlightened our students and faculty. Thank you, Sandeep. I would like to sincerely thank our Honorable Chairman, Thiru R.S. Muniratnam sir, for his constant guidance and encouragement, which makes such academic initiatives possible. Also, I would like to thank our Vice Chairman, Thiru R.M. Kishore sir, for his invaluable support and vision that inspire us to reach greater heights. Thank you, sir. I extend my gratitude to our principal, Dr. Anbuchalian, for leading us with his dynamic leadership, and to our dean, Dr. K.K. Tyagarajan, for his continued support in all academic activities. Thank you, sirs. I also wish to thank our HOD, Dr. K. Helen Prabha, for organizing and coordinating this event so effectively. Thank you, ma'am. Finally, I thank all the faculty members, students, participants for their active involvement, which has made today's session a grand success. With this, we conclude today's program. Thank you all once again. Thank you.
Thank you all for staying tuned with us. Also, the content is available in our institution channel for you to like and share. Subscribe to our channel and be in update about our institution happenings. This is Anita and team signing off. Happy Sunday.
Thank you, Sandeep. Actually, it's really very useful session. You know, we people, our students, they are getting trained with 5G core and datacom in the current semester, and this part is going to help them a lot. And I'm sure that I can students will be making use of all this thing, the topics that you have gone through, and that would be very much useful. And we would like to see you here in our college soon. When you come back to India, please visit our college, visit our department, and that would be very grateful for us. Thank you.
Thank you,
Definitely, sir.
Sandeep. Sandeep, when you visit your native place, please kindly visit our R.M.D. Engineering College and share your expertise to our students also.
Definitely, ma'am. I'm honored to present here, ma'am. Thank you.
Thank you so much.